session is yours.
Okay, great. Thank you, Moas. Yes, as you mentioned, my name is Pim van der Waa, and today I'm going to talk about the simulation of a 3D concrete printed object using finite element analysis. 3D printing becomes more and more popular. And, a lot of research recently has been done to 3D printing of concrete, and also numerical research is done at the moment. And we also are trying to do some research, let's say some numerical research in the topic. In this webinar, in this e-learning session, I will discuss two approaches to simulate a 3D printed object. I have the detailed approach and the practical approach. Already as the name is stated, the detailed approach, I will try to model it as detailed as possible. And I will try to take into account, for example, the aging of the material and also the nonlinear behavior, etc. But we also have a practical approach, which will be discussed in the second part of this webinar. This year in July, at the University of Technology in Eindhoven, there was a conference called Digital Concrete, and it was primarily about 3D printing of concrete and everything related to that topic. There we presented a poster, and that poster was awarded with the Best Poster Award. It was named Practical Approach to Assess Buildability of 3D Concrete Printed Objects Using Finite Element Analysis. And that poster will then be discussed indeed in the second part of this webinar. Okay, so the detailed approach. The detailed approach, we should take the following things into account. So we're going to indeed model, as they call it, extrusion-based printing of concrete. So that means, we're going to print it layer by layer. That's one important thing to keep into mind, because that determines how we set up our analysis, for example. And also the modeling approach we choose. Next up is the mechanical behavior of early age concrete. Since we're going to print fresh concrete, we of course cannot use regular behavior of concrete. We have to use early age behavior of concrete, and then in that sense really early age behavior, since we're talking about not in terms of days, but in terms of minutes or maybe even seconds. And also we need to take into account all failure mechanisms, and for 3D printing in general, that is plastic failure and or instability due to buckling. So first up is indeed the extrusion-based printing. Basically means that indeed you have the nozzle and it prints the concrete layer for layer, something like this, up to the top. So that means also in Diana we have to model these layers separately. That looks something like this. So we're gonna have to do we have to perform a phased analysis, as it is called. And we will start with just one layer, perform a nonlinear analysis for that. So that means just self-weight. That's the basic loading. And then perform a nonlinear analysis. Go to the second phase. That means we're going to add another layer, perform a nonlinear analysis. Again, add another layer until we have the full, in this case, cylinder printed, or until we see failure. Next up is the mechanical behavior of early age 3D printed concrete. Not too much is actually known about this young of an age of concrete. At the University of Technology of Eindhoven, they have done some research to this behavior. And in the article below of Rob Wolfs, early age mechanical behavior of 3D printed concrete, numerical modeling and experimental testing. And they have indeed done quite some testing on early age behavior. And on the right side, you see an image or a graph from that article. And it is the Young's modulus versus the concrete age. And as you can see that there's a linear relationship between those two. So we can see actually in the beginning it's still linear. So I also listed it down in the table. Furthermore, we just have the Poisson ratio and the density. Those are actually our linear material properties. Next up is the compressive strength. Also, the compressive strength varies, of course, in time. Also, the relationship is a linear behavior, so that means it will increase linear against time, similar as the Young's modulus. Oh yeah. Next up is how it will behave. Of course, we know in general from compressive strength. If you look at the stress strain diagram for compressive behavior, we in general look at a parabolic curve. But for very young, fresh concrete, this is actually not the case. You can see that here, if you look at a time of t is 0 minutes, it looks more like a sort of plastic behavior, or as we say, ideal plastic behavior. And that's also for T15 and T30. Actually, from when we look at around 1 hour, we see more or less this parabolic curve. So for me, I will just make it ideal plastic when I look at the material properties. Next up, they also did some testing for the shear strength. Also, the shear strength versus age is linear, at least the relationship between those two. Also, I will be using this as tensile strength. I just assume that it's more or less the same value, the shear strength and the tensile strength in this case. So how do we model this Indiana itself? So we're going to use a total strain crack model to model this behavior. The total strain crack models already have been set up that they can be made dependent of, as it called, maturity. And if they are dependent on maturity, they can be dependent on time. Because Diana is also known for young hardening concrete. And young hardening concrete is also related to time. Only, of course, you look more at days and not in seconds or minutes. But here you can see that we have the relationship between the maturity and the Young's modulus. And then the maturity is this expressed in seconds. It's a little bit same as you would relate it to element age. The same thing can be done for the tensile strength. We can also relate the tensile strength to a maturity, so that means we can relate it to time. And as you can see here, we choose for an ideal plastic tensile curve, as I discussed before. Same thing as for compressive strength, also ideal curve. So that means ideal plastic curve. And also, again, the compressive strength can be related to the maturity, so therefore it can be related to time. So how will my stress strain diagram look like? It will look something like this. So we just have the Young's modulus, a certain tensile strength and a certain compressive strength. At time is 0, for example. If we increase the time, so we go to the next time step, for example, T1, and we can see that our Young's modulus has become more stiff. Our tensile strength has increased, and also our compression strength has increased. And if we then go to the next step, it can increase, or it will increase further. And that's the way it works. Next up is the, indeed, we need to be able to describe all the failure mechanisms. So plastic failure can be described by the material nonlinear behavior. So that basically means the physically nonlinear behavior of concrete itself. And we also need to be able to describe the instability due to buckling. We can do that by taking into account geometrical nonlinearities. And with geometrical nonlinear behavior, we can describe second order effects such as buckling. In that article about the early age mechanical behavior of 3D printed concrete, which was written by Rob Wolfs, they also have a test case, of course, where they do an experimental test of a cylinder, and they just print all the layers until failure. On the left side, you can see that they have made some images, some visual images of 5 layers, 10 layers, 15, up to 30 layers. They have done a few tests of these cylinders, and in general, it fills around layer 29, they said. In this case, they have one where it fills after layer 30. So the idea is to model this experiment with keeping in mind the previous slides. So it's a cylinder of 500 mm with a thickness of 40 mm, and all the print layers have a thickness of 10 mm. And the print velocity is 5,000 millimeters per minute, so that means about 17 seconds per layer. And as you can see, we're using now first solid elements to model the cylinder. Here you can see the behavior, or at least I'm showing the deflection. Not too much is happening in the beginning. And then in the end, you can see it bending outwards. Also what you saw in these images, you could see actually up to layer 15, you don't see too much. And from layer 20, you can see that it is actually bending outwards. Layer 25, it's more pronounced, and layer 30, you can see it's indeed completely bending outwards. You can also see that in the Diana analysis. So indeed, if you look at on the left top of your screen, you can see the phase number that's equal to the layer number. So that means layer 32, that's the final layer, we see divergence of the analysis. So that means we see failure. You can also see that from like layer 15 to 20, we can actually see the deformation of the cylinder. And also here you can see then the time. And also here the maximum displacement. And indeed, we see actually exactly the same behavior as we see in the experiment. Only in our case, it's failing just after layer 31. And in the experiment, they fail at layer 29. So that's not too bad. So there's a few things we can check even more from the results. So one thing which is interesting is to see the time effect. So this is a time layer 31. So that's time is 527 seconds. You can actually see that the first layer indeed has an age or a maturity of 527 seconds. And the top layer has an age of 17 seconds because it's at the end of the step and each layer takes 17 seconds to be printed. So you can see nicely the linear distribution over the height. And you can also see it back in, for example, the Young's modulus. So for example, this was the Young's modulus. We started with a maturity of around 78,000 Pascal. You can see here that's a little bit higher because we start at 17 seconds. And if we look at 500 seconds, we're more or less here. So that's maybe a little bit below 90,000 Pascal. You can also see that here in the graph. So that's around this value for the bottom part. Yeah, in the next slide, I'm actually showing on the left side the evolution of the compression strength. And on the right side, I show SP3. And SP3 is actually the largest compressive stress in my model. So that basically means the compressive stress. What you actually see is that in the left, it's starting around 6,000 and it's slowly increasing to around over 7,000 Pascal. And on the right side, you can see that it's indeed starting with a relative low value because that's only the self-weight, very low, and that is indeed trying to catch up with the compression strength. And from some moment, we can see that indeed the compressive stress in the bottom becomes actually equal to the compressive strength. And then we see plastic strains, and in the end we see instability due to plastic failure together with buckling. So it's actually combined failure mechanism in this case. If you look closely, you can actually see that the compressive stress becomes actually larger than the compressive strength. In theory, that's not really allowed. But in the last few steps of the analysis, the convergence behavior was already a bit, we had some problems with finding proper convergence. So it already showed that the behavior was a bit unstable towards the end. That also probably explains that why it can also fail a little bit earlier than layer 32. Also the fact, because you can see here, this is the strain. Actually, not too much plasticity is occurring, only at the toe here. So due to plastic deformations at the toe, we can see that the buckling is more, this is actually causing the buckling in the end of the cylinder. What you do see is that we only used, actually only, you can see here, we only used 2 elements over the thickness. And that's probably also one of the reasons why the convergence behavior in the end is a bit poorer, because actually this is not enough to describe buckling over this thickness. In general, we should advise you to use around 4 elements over the thickness to describe buckling. But in this case, I only used 2 to speed up the analysis a little bit. But this is probably also one of the reasons why the convergence is a little bit worse towards the end. But in the end, we are quite well capable of describing the correct failure mode and also failure load. So that means the layer to which it fails. Also, the model gives us quite some nice insights on how for example, how the compressive strength is developing related to time, and also how the stresses are developing in the model. The only thing is that was also, the analysis time is, I think, relatively long. 15 minutes, maybe not as a checking analysis, but this is still a relatively small model. It's only a cylinder. It's not an actual structural part. And also the fact that we should have used actually maybe 4 elements over the thickness to describe the proper buckling. The analysis time could be even longer. So we were thinking of ways to speed up the analysis time. And one thing we can try is to use shell elements, so curved shell elements, instead of using solid elements. And it has the benefit that we have little, or at least fewer degrees of freedom. And also we can choose indeed the number of integration points over the thickness to describe the buckling. In this case, I also chose 5, which is a little bit on the low side, maybe. Maybe you, 7 is also okay. But in this case, I used 5. yeah, we can also see what happens here. In general, I think we see pretty much the same behavior. So also on the, we see this same collapse mechanism. And if you look at the number of layers, in this case, it's failing a little bit earlier. You can see it's failing now at layer 29. So it's actually better than we found with the solid model. But the behavior is more or less the same as we see in the solid model. So we can check the results a little bit further. And we indeed see that we reach, yeah, and I have no picture in this case of the compressive strength at that time. But if I would check the compressive strength at time 476, I will find this value because this model had much less problems with converging. And in the end, we see indeed also plastic strains and the plastic strains at the outer layer. So not the inner layer, but in this case, we're showing the outer layer. It's indeed also causing buckling in the end. So due to that little bit of plasticity in the toe of the cylinder, it's indeed helping buckling to the elastic buckling as a failure mode. So pretty much the same concluding remarks. Also in this case, we are able to predict the correct failure mode and the failure load. And we also get some insight from the failure mechanisms and the stresses, etc. The analysis time is now reduced to 4 minutes approximately. So that's already a bit better. However, if I would be a designer and I would be designing some sort of column in a 3D printed object, as a 3D printed object, in this case, that still could be relatively long if I would change my design constantly and see what will be the best fit. And 4 minutes can still be quite long. So I was thinking of a more practical approach. That is what we're going to discuss now. The practical approach is actually based on the fact that most of the collapse, actually almost all of it, is due to elastic buckling and not to solely plastic failure. It can be a combination of the two, like some plastic failure or at least plasticity with buckling. You saw that also in the cylinder. But in general, it is buckling which causes failure. So the first idea is to perform a Euler stability analysis to check the buckling load for every layer. You can see it here on the right side, this image. We now have 10 layers. And we see that we have a buckling value of 3.13. That means that the 10 layers can withstand 3 times the self-weight, or at least a little bit over 3 times the self-weight. So that means actually that it's still sufficient. Only when the buckling value becomes below 1, that means it cannot withstand its own self-weight anymore. So for example, if we go to 11 layers, we can see that the buckling value is now decreasing a little bit, up to 12 layers. And in this way, we can build up the entire cylinder until the buckling value is below 1. Now we know also when our cylinder will fill. Now this method has a few benefits. First one is that we're only performing linear analysis, and those are of course really fast. And also we need fewer material input. We're only inputting a Young's modulus, a Poisson ratio, and a density. On this slide, I basically wrote out, or at least presented the flow charts which we're using for this practical approach. So basically, we're starting with the input is a finite element model. You see that on the left side. And we start with, from the bottom, we start with a number of, in this case it's called and not layers. In general, we start with like 5 layers. No need to start with only 1 layer because that will never fill. So we start with like 5 layers, perform the Euler stability analysis. We check the buckling value. When it's larger than 1, we check whether all the layers are printed. If not, we will increase the number of layers. The idea is not to increase it one by one, but we can check how large our buckling value is. If our buckling value is very large, we can still, of course, we can just increase it with 1 layer, but then it's not going to change too much. So there's an algorithm in there to go, when the buckling value is rather large, we also increase with more layers. So indeed, we increase the number of layers, and we then perform again the Euler stability analysis. And then we check whether the buckling value is larger than 1. And if it is, we can check if all the layers are printed. And when that is true, we don't have failure. If it's lower than the buckling value of 1, then it's false and we have failure. That's the procedure we're going to try. I did that for this cylinder. So in this case, we started with 5 layers and we got a buckling value which was 11.6. So in this case, we could actually add quite some layers already in the second step. So we added some layers, and then we see a buckling value of 1.8. After that, it increases a few more layers. And when we get closer to 1, we only add 1 layer, of course. Up to failure, which is now at layer 28, because then the buckling value is lower than 1. So it means in this case it's failing at layer 21. Oh, sorry, 28. And that's the procedure we're using. In this case, the analysis time was only 40 seconds. So in 40 seconds, I knew whether I could print the cylinder or not. That's already quite fast, I think. There's only one question, or at least it's one important question, is what do we do with the Young's modulus? Because if we choose a Young's modulus of 1, actually we assume that there's no nonlinear behavior at all in our specimen or in our finite element model. So I would call that more or less an upper bound approach. Like for the cylinder, we could see that there was quite some plasticity in the toe of the cylinder, or at least at the edge at the bottom of the cylinder. So then it would make more sense to use a little bit of like half a Young's modulus or even 1/3 of a Young's modulus. It's a general rule, I think, for engineers to use 1/3 of the Young's modulus if we want to model concrete just as a linear material. So I think that's more or less like the lower bound approach. So to test this approach a bit better, I came across this article. I also saw this presentation at the FIP Symposium in Krakow. They are actually presenting benchmark structures, which you are going to print experimentally. And then you can check with your finite elements simulation whether you can find the same solution as your experiment. So for example, we have here on the left top side, you have the cylinder. I think it was something like 250 diameter, and the solid line shows until which layer it can be printed until failure. In this case, it looks something like layer 38, and then it fails. And in their case, their finite element analysis was able to print the entire structure, for example. Then we have the ascending cone. They have 3 ascending cones with different diameters, and they were all able to be printed. They have the descending cone. Actually, they only printed 2, so the 150 diameter and 200 diameter, and both of them were not able to be finished. And they are also printing 2 domes. You see 3 here, but only the solid lines are actually experimentally printed. So the idea is now to test how well I do with my practical approach. So I will compare it only, of course, to the experimental testing. And for this approach, I will be using the lower bound approach, so only 1/3 of the Young's modulus, and see how close I come to the results. Yeah, these are the results. On the left side, you can see the experimental, so the 3D printed concrete. You can see here, for example, the cylinder of 250. The idea was to print 60 layers, but at layer 39, it actually failed. And this is then the Diana analysis. This was using the practical approach. In our case, it was failing at layer 33. Then we see the 3 ascending cones. So those are, yeah, that's B. So basically the diameter is shrinking once we go higher. In the experiment, all 3 of them could be printed. With the practical approach, actually only the first 2 could be printed, and the 3rd one fails at layer 35. Next up is descending cone. It fails at 29 and 30, and in our case it fails at 22 and 25. And last up is the dome. We were also able to print a dome, the small one, and the last one failed at a similar layer. So in general, I think this practical approach works quite nicely. Yes, also if you look at computational time, I think this one was indeed around 40 seconds. But if you look at the dome, there's only a few layers. I think that was within 20 seconds. So that's then, of course, relatively fast that you can check whether your design is sufficient or not, just as a first check. Just as to conclude. So the detailed approach, if you would want to use that, we can capture the correct failure mechanism and the correct failure mode. Also the correct failure load, so that means at which layer it will fail. Only thing is, of course, the analysis time is relatively long. So it's best used basically as a final check. So when the design process is more or less over, or when you are in the final stage, then the design is not changing constantly anymore. Then it makes sense to use the detailed approach. Also, probably you have more information about the mechanical properties. So it makes more sense to use it as in the checking stage. Then the practical approach. The practical approach is of course based on elastic buckling. So it does capture elastic buckling quite well. It's relatively fast. And when you use the lower bound approach, is of course a little bit more conservative, but it still describes the behavior quite well. And I think this is then best used during the design process when you're more changing your design.
Thank you very much and have a very good day.